Screen there.
All right.
Thank you. Enjoy the day.
Thank you. And welcome to Medieval Mathematics. We're going to overview mathematics in the medieval period from 600 to 1600 AD. I mean, the time distinctions don't make a whole lot of sense outside of Europe, but oh well. So what we're going to come out of this class with is you're going to have an understanding of the numerals and notations that were used for mathematics worldwide. You're going to kind of understand what people were able to do with that mathematics, and you're going to be able to kind of track changes that allowed these to evolve into the system that we have today. So it's going to look a lot different in 1600 and even in 600 than it does today. We're going to look at how different it is. Just to give us some background as to what math can do for us, I want you to understand that math is a technology. And when a bunch of people have the same mathematics, they have a shared technology. Mathematics is, we like to think of mathematics as like this, truth with a capital T, right? It's something that's always the same. It's constant. This is a cultural idea about mathematics. And it's unique to our culture. Mathematics is interdependent with other technologies that a culture has, and there's a feedback loop there. The math that you can do affects your technological development, and your technological development affects your mathematical development as well. People tend to develop math that will help them to do what they need to do. And just a couple of quick terminology things. We're going to talk about numerals, numbers, and digits, and these are three different things. So a number is a cardinal quantity, like I have 2 fingers pulled up here. Okay, that's number. That's 2. A numeral is a symbol that represents that cardinal quantity. Then when you write that 2 on a paper, that's a numeral. There's nothing 2-ish about that numeral. It's just a symbol that we are using to represent the concept of 2. A digit is a symbol that's used as part of a numeral. So like the numeral 29 has a 2 in it. That 2 is serving as a digit. And in fact, 2 is one of 10 digits called decimal digits because it's base 10. Our numeration system also has a quality that's called positional. Okay, it is a positional numeration system. If it can represent a different number based on its position, that means the numeration system is positional. Not all numeration systems are positional. We're going to see that in a minute. Also, 0. We're used to 0 being a numeral, a number, and being able to use in computation. So you can do, it makes sense to do something like 0 times 5, okay? In our system, 0 is a placeholder and it's a computational 0. A placeholder 0 is used in a positional numeration system to show that there's an empty position. Like in the number 205, there are no 10s. That's what the 0 there signifies. And the placeholder and computational functions of 0 are 2 separate functions of 0. Our 0 does both. Not all zeros do. So the system that we have now, just to kind of sum up, it's a base 10 positional place value system. We have a placeholder and a computational 0. We have 10 distinct digits. They're abstract symbols. Despite the people who try to, tell you that 2 actually, they put the dots on them. I don't know if you've seen this system that they show to kids. Yeah, that's not original. That's somebody invented that recently. We have algebra. We have a symbolic notation with which we do algebra. We have these, these symbols that we use. We have letters for unknowns. We have fractions in any denomination. We have roots of any index. We have cube roots, square roots, fourth roots, fifth roots, things like that. some of that did not exist in 600 AD, especially the symbolic notation. So let's take a look at kind of a snapshot of what 600 AD looks like. So in Europe, they're still using Roman numerals, and they're using finger numerals, which we're going to see in a minute. We're going to see all of these things in a minute. In Asia, they had stick numerals and glyph numerals. In India, they had the precursors of the modern numerals that we have today. And Hebrew and Greek were very much concerned with numerology, with making a correspondence between words and numbers. And in Mesoamerica, we have a very well-established system of base 20 Mayan numerals. As far as computation goes, most computation was done on an abacus of some kind. This is because we did not have the symbolic computation that we do today. And there's lots of different kinds of abacuses or abaci. I don't know what's the correct plural of abacus. I should look that up or have my word geek husband do it. Anyway, we had a lot of different devices for doing computations, for doing arithmetic. As far as what people could do mathematically, pretty universal. People could do arithmetic, fractions, solve linear and quadratic equations, provided that they had real roots. They didn't have imaginary numbers back then. Basically, everything you would learn in your high school algebra class could be done at 600 AD. It just looked different than it does now. Mesoamerica is a little bit different because they had an independently developing civilization. They were not in trade contact with Europe, India, and Middle East and Asia. They were all in trade contact with each other, but Mesoamerica was separate. So they did with their arithmetic, they did addition, subtraction, multiplication, and then rather than division, they did ratios. So a little bit different. Okay, 1600 AD, here's where we end. We have the Hindu Arabic numerals. They're the same like our modern ones. They're, fonts are different, but, but they're standardized and they're prevalent. They're all over the world. Numerology is still in use as it is today. Computation, people are starting to do symbolic computation on the regular. But they're still also using abacuses because their abacuses are handy and you don't have to have a paper and pencil. You just have to have your abacus. Algebraic notation is also becoming popular. It doesn't look like it does today, but it was starting to be used. As far as what people could do, by this point, people could solve cubic equations. Europe had just figured them out like less than 100 years before. The Chinese had them figured out centuries before that. Trigonometry was starting to become a thing. Trigonometry originated in India. Analytic geometry. Now, this is a concept that we think of as commonplace today, but it was cutting edge technology in 1600. Okay, analytic geometry is where like you have a quadratic equation and you see the graph of a parabola and you say these are the same thing. That's what analytic geometry is. That was bleeding edge technology in 1600. We're also starting to see the invention of calculus and probability as branches of mathematics. Questions? Any questions so far? Okay, I'm going to ask you to mute yourself. I'm hearing some dings in the background. So if you are not talking, please mute yourself. And if you have a question, please feel free to unmute and ask. So let's take a look at some of the numerals that were in use during the medieval period. First of all, there's the familiar Roman numerals. And if you ever when you were in school and they taught you Roman numerals, did you ever wonder how you could add stuff with Roman numerals? How you could do like arithmetic with Roman numerals? The answer is you can't. It's a base 10 system, but it's not positional. So like, for example, let's take a look at I mean, a V always means 5, regardless of where it is. Okay, in there. And I always means 1, regardless of where it is. It's both additive and subtractive. So additive means you're adding things up. So when we have VI, that means we have 5 plus 1 gives us 6. Okay. It's also, however, subtractive. Look at IX. It's when a number of smaller, a numeral of smaller value comes before. When a numeral, I accidentally clicked on my screen. When a numeral of smaller value comes before a numeral of bigger value, it's subtractive. When it comes after, it's additive. And it makes it difficult to have higher numbers because you have to have a different letter for each it's base 10 with a sub base of 5. So you have to have a different letter for each time you hit the sub base. Hebrew and Greek used letter numerals, and this is what made numerology really, really easy for them. Basically, rather than use separate symbols, they used letter symbols for numerals. And of course, that created some complications in Hebrew, especially because certain number combinations would produce words that were sacred, and so they would have to substitute a different one. But the basic idea is that letters represent numerals, and so combinations of letters can create numerals by adding them. And then there's a correspondence between numerals and words. So you can take a word and add up all its number values and get a number, and you can find other words that have that same number value because they're not unique, and then you can equate those two words somehow. So this was done in period. So finger numerals were used a lot to overcome language barriers because words for numbers are different in different languages. Finger numerals were kind of used for trade. And you could also hide them under sleeves and read them by touch. So you and the other guy could put your hands like this and do finger numerals to offer each other to negotiate the offer, and then no one could see what price you had agreed on. So there's actually an ancient dirty gay math joke about these finger numerals. I would draw your attention to the second column as I tell you the joke. The joke is that the man went to the market with 90 and came back with 30. Okay, if you're not asking a question, please mute yourself. Thank you. Okay, the Chinese had stick numerals. It was a base 10 system with positional numeration. So you can see these are the different positions here. These are numbers that indicate the different positions. They also did decimal fractions. So you'll notice that this is the ones column, okay? There's like a tens column and there's a bunch of different columns, okay? This is tenths, hundredths, and thousandths. It's kind of backwards from what we would think of. So they used a grid for an abacus, and you'll notice that the orientation it varies from square to square. So like you'll see vertical orientation and then horizontal in the next square, vertical and then horizontal. The Chinese had a very sophisticated mathematical system long before a lot of other cultures did. Over to Mesoamerica, we were using a base 20 system using a sub base of 5. So the Mayan numerals, you use a dot for 1, 2 dots for 2, 3 dots for 3, 4 dots for 4, and then a line for 5. And then so each line represents 5, and it's additive. They also had an alternate system that was not purely base 20. They had the second column be 18 instead of 20, and that enabled astronomical calculations. Hindu-Arabic numerals. These are the ones this shows the evolution of the numerals that we have today. These were the original in the 1st century AD. So about the time that we're looking at, they look like this. This is what they look like. Notice there's starting to be a 0. It starts off as a dot or an open circle. These were originally influenced by the Chinese stick numerals, as you can see over here. The 1, the 2, the 3. Okay, it's fairly easy to see the influence of the stick numerals there. The Hindu Arabic numerals arrived in Europe through the Muslim world in Spain. In fact, about the year 1000, people thought that these numerals were devilish because they came from Muslim civilization. And people today still think that they are. You may have thought that about your math classes. So let's take a look at computation and algebra. Any questions about numeration before we move on?
You said that finger numerals were used a lot in trade.
Yes.
How widespread was that?
Fairly widespread. And this kind of communication was used anciently, but that particular finger numeral chart is after the work of Pacioli, which is, gosh, I can't remember which century, like 11th, 12th century. I mean, it's a modern diagram, but he wrote about them. So, but it was more of a trade thing. You can't really do arithmetic or any kind of a system like that with finger numerals. More questions? Okay, let's take a look at computation and algebra. So this woodcut from the Margarita Philosophica kind of illustrates everything that was wrong about Western mathematics. But let's take a look at it. Okay, so what we've got here, this lady is representing arithmetic, and she's judging a contest between Boethius and Pythagoras. And you'll notice that they're using different technologies, different mathematical technologies. Pythagoras, who, if you take my next class, you'll find out that he really has nothing to do with anything mathematical, but he's using a counting board like this one. We're going to take a closer look at the counting board in a minute. And then Boethius, who existed before the advent of Hindu Arabic numerals, is using Hindu Arabic numerals and fractions. And he's doing symbolic computation. And so this is a contest between them, and based on the figures that are on arithmetic stress, you can tell who she really likes. She really likes those Hindu Arabic numerals because they're making it easier to do arithmetic. So let's look at how people did computations. The thing that they used mostly in Europe is a counting board, and you can use this kind of thing dates back pretty far before the medieval era, because this is how you do addition in Roman numerals. The Romans also had a sliding bead abacus, which I'm working on a class called Practical Abacus, which is kind of going to kind of give you a tour of how to use abacuses around the world. But for today, we're just going to look at what these things are. So this is a counting board, and you're going to place, you can see in the illustration of Pythagoras that there's counters placed on and between the lines. A counter placed on the line indicates that number, and a counter between the line indicates 5 of that number below it. So the counting board could take any form. It could be actually etched into a table. There are tables that have these counting boards etched into them, or painted on them, or something like that, inlaid, whatever. They could also be painted on fabric, and so you could have a portable fabric counting board that you could just roll out on any surface and start doing your math. Some of the highlights of some of the different abacuses, abaci. This is a soroban. It's a Japanese abacus. You can see one on the bottom of the picture, and then the one on top is a swanpan. That's a Chinese abacus. And notice that they're very similar, but they have different numbers of beads. The Chinese swanpan has the extra beads, and they allow for hexadecimal calculations. They had a base 16 money system. And so occasionally, even though they were primarily base 10, they needed the base 16 computational capability, and that's what the extra beads, the extra, notice they have 2 of these, what are called heaven beads, instead of 1, and they have 5 of the earth beads instead of 4. The Aztecs had the Nepohualtzintzin, and this is my Nepo. The Chinese abacuses have sliding beads. These have flipping beads. They flip towards the center when they're in use, and they flip away from the center when they're not. You can use them in decimal mode, but it's definitely set up for vigesimal or base 20 system. And they have 91 beads because 91 times 4 is 364. So they were able to do calendrical calculations on this. In South America, they have a couple different devices that are in use, or that were in use. The Upana is a South American counting board. That's this right here, and you'll notice that it's 3D. Each level is a higher place. Each higher level is a higher place value. Also, this is a kind of a Incan spreadsheet, the quipu. It's made of knotted strings, and they did not know what it encoded until recently. It's very recently, like in the last few years, the code of the quipu has been cracked, and they basically discovered that it's a spreadsheet. It has tax information and things like that in it.
Mm.
You have a question or observation? Okay, let's look at fraction technology. So before the decimal fraction was invented, Egyptian fractions were used. These are fractions that have a numerator of 1. The only exception is they have a separate symbol for 2/3. Okay, and anytime you have a fraction that doesn't have a numerator of 1, so like what we would call today 3/4, you represent it as a sum of fractions with a numerator 1. So 3/4 would be a half plus a fourth. There's a theorem that you can represent any fraction with no more than 4 Egyptian fractions. So this naturally was a lot kludgier than the system we have today, which is why we abandoned it when we had the system we have today. And basically, if you want to add fractions, multiply fractions, whatever, you have to go look up on fraction tables. And it's really kludgy, and it takes a long time. And we can find them in papyri that we have from ancient Egypt, these tables. Fibonacci was still using them in 1202 AD. Algebra, the word algebra itself comes from the classic algebra textbook. I'm not even going to try to pronounce that, but it means the compendium.
Excuse me, milady.
What's that?
What is the Could you go back one page for a sec?
Sure.
What is the difference between ratios and fractions?
So a ratio, there's not a whole lot of difference mathematically, but it's thinking, it's more a shift of thinking, because we can think of fractions as ratios, right? We're used to that because that's our system, and that's what we train kids to do in our society, is to think of ratios and fractions as the same thing. But writing a ratio as 2 to 3 instead of writing 2/3, they're not conceiving of that as a division like we would. Does that make sense?
Are you saying that it's more like something is twice as much as something else rather than looking at it as a whole?
Right. So like, for example, if I have a recipe for secondibin and the ratio is 4 to 2 to 1 of water, honey, water, and vinegar, okay? So I'm not thinking that I'm going to use 1/4 as much vinegar as I do honey. Okay, you see what I'm saying? That's thinking as a fraction. Whereas a ratio is like, I have 1 part of this, I'm going to make 2 of that and 4 of that. It's a difference in thinking. Does that make sense?
Yeah.
Okay. Okay, so let's talk algebra. So even from like Babylonian times, we've had the ability to solve systems of 2 linear equations in 2 variables. Okay, Diophantine equations, which is one equation in two variables and has multiple solutions, those have been solvable since long before the medieval period. But we didn't do them with symbols like we do today. Every problem was a word problem. And you had to solve them through word reasoning, verbal reasoning, rather than through symbolic manipulation. As far as like what equations could be solved, quadratic equations also have been solved since ancient Babylon. Brahmagupta invented the quadratic formula, but because he didn't have imaginary solutions, it would only produce positive real solutions if they had them. As far as like putting together the quadratic formula with the imaginary numbers, that's Simon Steven in 1594. So that was bleeding edge technology in 1600. The Chinese could solve cubic equations by the 2nd century BC, at least some of them. They could solve general cubics and some quartics by 7th century. So they had the capacity long before the race for the cubic in the 1500s, and that's a whole other story that's really funny and involves getting somebody drunk. So that's a whole other presentation.
Excuse me, I
Yes.
can't find my hands up thing, but do you have a specific example of a equation being presented as word and solved by any chance?
I do, but I don't have it handy.
Well, maybe I'll email you later.
Yeah,
so you
email
can-
me later and I'll email you back.
Thank you.
No problem.
By the way, where is my hand raising thing?
I don't know, and I can't see hand raises while I'm presenting, so that's why I have a TA.
Okay.
It's under reactions. What about differential equations? Do we have to go to calculus first?
You have to
before
get
we there?
calculus first before you can do differential equations. And calculus is being invented at the end of that period, so. I haven't included calculus in here. Well, let's talk a little bit about calculus, though, about what we can include in the medieval period. So what we now call Maclaurin series, they were actually first discovered in India. They had like tests for convergence of series, and they were able to use series to approximate values for like pi. So they had all of these things. They had the sum of geometric series, Taylor series, what we now call the Leibniz formula, because everything in math has to be named after a dead white guy. They were able to get accuracy to 9 decimal places, and they had a system equivalent to Newton's system of fluxions, which is the foundation of calculus, basically. It's what calculus is based on. So they almost had modern calculus in period in India, but not in Europe. As far as the modern algebraic notation, let's take a look at kind of the evolution of that. All of these pieces that go into our modern notation, the fraction bar is the oldest of them. It dates to the Islamic Golden Age. 14th century was when the plus and minus signs were invented, and you can see those in the document picture that I've put here. The 1500s saw a representation of the variable with a symbol, and they used CO, which is short for cosa, which means thing, CE, which means senso, which is as short for the square of the variable, and CU or cubo for the cube of the variable. So that's when they started to do that. They're not using X yet. That's a much more modern invention. But they did use a symbol or some kind of thing to represent the variable rather than a word, rather than like an entire word. We're saying the quantity you want or something like that, like they used to do. They're now using the symbol CO. So you would see, you know, COP, CU, or C equal or equalis 5 or something like that. And that means, you know, X plus X cubed equals 5. The radical sign was invented before the equal sign. So to get square roots. The equal sign, we're getting into the late 1500s now. We get the equal sign, decimal notation, modern algebraic notation, and finally, after the period, the multiplication sign that we use today. So that kind of gives you an idea of the evolution of that. Any questions before we look at geometry?
How widespread was the equal sign if it was only invented in 1557?
The symbol for the equal sign was invented in 1557. The concept of equality is ancient.
Ah, okay.
So they would use a word to describe it rather than a symbol.
Thank you.
No problem. Other questions? All right, let's take a look at geometry and trigonometry around the world, and we're just going to take a quick tour. If you want some more detailed information, I have a class coming up in the next period that's called Here's Looking at Euclid. And that's going to go into more depth, but we're just going to kind of give an overview here. In antiquity, people knew Pythagorean triples. And the Pythagorean theorem itself was known 1,200 years before Pythagoras. But you know, it's math. Everything has to be named after a dead white guy. Geometry was more practical than theoretical. It had to have a purpose. Okay, it had to be something you could use for engineering, architecture, or surveying. Okay, they're not doing 2-column proofs. This is actually not a 2-column proof here. This is a table of Pythagorean triples in cuneiform. In ancient Greece, that's when they developed theoretical geometry where you're doing proofs. And they didn't do 2-column proofs either. That's a more modern invention. Their proofs were verbal. And they literally used geometry to measure the earth. They discovered irrational numbers, and then, of course, Euclid. Okay, so Vedic geometry in India. This is the first known written statement of the Pythagorean theorem as a theorem. There's a difference between knowing that 3, 4, 5 is a Pythagorean triple and being able to have a formula that you can generate or solve triangles with. So the Indians had that Pythagorean theorem as a theorem. Also, they would use geometry mostly to lay out ritual altars to make sure that they were perfect. Later in the period, between 400 and 1600, they developed the trig functions, sine, cosine, versine, which is one we don't use today, tangent, secant, and arcsine. They had trig tables. They had trig identities. And an interesting story is how the names of the trig functions came to be. So let's look at sine. In Sanskrit, it's ja, and it's actually 2 times the sine. It's what we would call the sine today. This is 2 times the sine. It got transliterated into Arabic as jiba. But jiba is a meaningless word in Arabic. It was transcribed without vowels because Arabic doesn't use vowels as jub, basically. And then when other people saw that manuscript and tried to make sense of it, they figured this was the word jaib, which means pocket. And that word got translated into Latin then as sinus, which means a cove or a bay. You know, it's an indentation. And that's where our word sine comes from. It comes from a mistranslation of the Sanskrit. They also developed some pretty good astronomy and astrology and were able to predict eclipses and things like that. Chinese geometry and trigonometry disfavored proofs and theory. They wanted engineering applications. They knew all the area and volume formulas that we use today and ones we don't use today that were very useful for engineering and surveying, and they had spherical trigonometry. Arabic geometry built on the Indian geometry and the Greek geometry. So it was kind of a synthesis of both of those. We don't have time to go in depth on that, but Thabit Ibn Qurra, whose books are still in use today. I have a former student from Iraq that told me that her father had a copy of Thabit Ibn Qurra's geometry textbook. He generalized the Pythagorean theorem, and the formula that he has is very similar to the one we use today to generalize the Pythagorean theorem to all triangles, which is the law of cosines. It's actually equivalent. I proved it. I have the proof somewhere over there. They also developed astronomy and astrology, which were the same thing for a long time. What questions do you have?
In the chat, we have a thing that says, what is a two-column proof?
Okay, if you do not know what a two-column proof is, count yourself lucky. We were tortured with them in geometry when I was in school. Basically, it's you have to do a geometric proof, and they give you two columns, and you have to put each step in the reason why, each step in the reason why, each step in the reason why. So if you don't know what it is, you were never tortured with them as a child. Formulas for geometry that we don't use today, things like the volume of a frustum. So a frustum is a cone with the top chopped off. Think of a fez. That's what a frustum is. So there was a formula for the volume of that. That's an example.
Could you talk about the development of probability? You said that it was around in the 1600s.
Yeah, it was starting to be developed. And of course, probability was invented so that people could win at cards. Like I said, mathematics and technology interact, and people invent mathematics that they need for the purposes that they want it for.
And were they working like with conic sections and things like that?
Yes, so conic sections have been known since ancient Greece. And in fact, many books were written by ancient Greeks on conic sections. Let me back the slide up real quick to show you. There it was. This is actually a page from Thabit Ibn Qura's translation of Apollonius's conics from ancient Greece. So yeah, a lot of things were known about conic sections that we do not teach today in schools. Mostly because the Greeks took a different approach than we do. We take the analytic geometry approach, which is that there's an equation and there's a conic section and they mean the same thing. Yes.
You have 10 minutes.
Okay.
And before we go on, let me ask, everybody make sure that you put your name in the chat, because that will be going to the university. And that way they will have a record of the classes you have taken.
Okay. Kuniganda asks, now that they understand what the Kipu was recording, does it mean we understand how it works? Yeah, we understand like how to make the knots and things like that. There is research on that. I have not reviewed it yet. I'm working on currently researching for a series of classes on practical abacus. So how you can use an abacus. My goal is to get everybody at gate using at least one person at every gate using abacus to calculate people's site fees. Okay, what other questions?
I had a question.
Yeah.
It's like, how is the academic process of learning mathematics different than what it is now?
So I can only speak to Europe for that one because that's all I've done research on yet. I'm still working on some other cultures research, but first people were taught arithmetic, and arithmetic knowledge was actually fairly widespread. People who were tradespeople had to be able to do basic arithmetic to sell their bread and whatever. But as far as like symbolic computation and things like that go, that was like algebra, things like that. Algebra and geometry were more higher level stuff, and they did arithmetic differently than we do today. oh, I can't remember the name of the guy, Robert Record, I think it was. I was reading a biography of him and or a text that he wrote. And he shows they also taught doubling and halving skills, which we do not teach today. And he has an algorithm for you that basically means you have to know your times tables up to 5 times 5 rather than 10 times 10. And then you can work out what the rest of them are using this little algorithm. That's pretty cool. And I did a proof of that when I read it.
Okay, thank you.
I have a facetious question.
Okay.
So if what's that word? The science of probability was starting. Is that an excuse? Is that a is not learning that the reason that games like Pharaoh continued up into the 18th century, or the reason why it did?
That I don't know. The interaction between probability and games is not something that I've studied. Mostly because it's out of period. I'm focusing my research on in period, but yeah, that would be an interesting question to explore is how knowledge of probability affects games. I'm going to venture a guess that it doesn't affect games very much. And the reason why is because people still go to Las Vegas, even though you can prove that the house always wins.
50.5%. I was going to, because Pharaoh is related to games and period antecedents. That's why. Yeah.
Okay. Yeah, probability is hard. It's one of the more counterintuitive branches of mathematics. It's right up there with logic. It's really hard to wrap your head around probabilities and to like calculate them in real time. So if you can do that, more power to you. Go to Las Vegas, win some stuff. Any other questions? Well, I've got a question for you if you don't have any more for me. Go ahead.
This is super cool. And I think that this is so much of what we teach our kids. I also teach math in the Southern Islands. So much of what we teach our kids comes from the old white dude point of view. Can you share the bigger slides? Could I email you and ask for them so I could show my kids some of these, like my students?
Yeah, I'll share them with you. I'm trying really hard in my research to focus on expanding the knowledge of mathematics past the old white dudes.
5 minutes, m'lady.
Okay. Yeah, Hypatia is a ancient Greek mathematician. I've got a question for you guys. If you wanted to see more on one of these topics, which one would it be? Like if you wanted me to teach another class, I got the geometry one, but what would you like to see expanded on? I know that whoever is named Lucifer would like to see one on probability.
I would love one on calculus. I'm an engineer, so like I would love to have the understanding of how calculus helps with engineering and some of the expansion of that. Because we start to see a significant change right at the end of period, where we start using, don't need to go to partial differential equations and predictive.
Please, you're giving me a headache all
but calculus would be fun. But I would probably be one of the few people being in your class, but I would certainly attend.
Oh, what you say, just to tell everybody, I graduated high school in 1969. I was not allowed to take Algebra 2. My mother graduated college 1942 and became an accountant because women were not allowed to be engineers. Think about it. 2 generations ago, women were not allowed to be engineers.
Yep. We had to teach it ourselves or break the molds.
Now,
and women got us to the moon.
And my son went to a science and math college where 1/3 of the students were female. And I tell every one of them about my grandmother, about my mother. And I said, that could have been your grandmother. Think about the impact it made on those young women.
Now, I graduated from high school in '68, and I took, well, we didn't have calculus taught in my school, but we had all the algebra and the trig and all that. And I ended up majoring in math in college.
I went back for a math degree in my 40s because I wasn't allowed to take that stuff.
Well,
I
I
was
went
just,
to, yeah.
Well,
I was just going to say that my mother was in the same situation where she was born in 36. So in 1950, women didn't go to any sort of mathematical training. And the worst part is when she was in her 50s and she talked to me about how much she loved math. And I encouraged her to go to, college to do something about this. She said, no, it's too late. That's how read in the problem was, how burned in. Anyway.
I lucked out. I mean, I've been an engineer for 30 years, so, but I had a dad who believed that women could do anything. And the current Governor General of Canada was the person that he inspired to go back to do her master's of engineering, and why she became an astronaut with NASA. So my dad has been fully, as a guy with a math and a physics degree, and not an engineering degree because he couldn't do that part-time. Definitely thought that women could do math and encouraged me because I could do math, but I couldn't spell to save my life. So.
Oh.
That's what the spell checkers are for.
Yeah, now there's spell checkers. Back then there wasn't a spell checker.
Please make sure your name is the name you registered for the class under is in the chat. You're not sure, put it in again. Thank you.
Thank you very much, everyone, for attending. This class would be nothing without you. It would just be me talking to myself.
Teacher, I have one last question.
Yeah.
You first, ma'am.
When I have an interest in maths and sciences, but sometimes it's difficult to find classes on it.
Mm-hmm.
And there's a lot of ideas in chat of some really interesting classes, and you have some interesting classes. So how do we find out when you are teaching next?
Do
you have a newsletter we can subscribe to
right now, other than these? I do want to take a summer break. I teach professionally, and I would like to have a summer break. I signed up for this because I was supposed to teach these in person when we were supposed to have the Known World Science Symposium in Utah, and that didn't happen. So, so I'm teaching them here now. But I would love to expand my work and teach at different collegia. So, friend me on Facebook. I'm MKA Sarah Brilliant Thomas.
Put it in the chat, please.
Yeah, I'm putting it. Give me a second. I'll give you the link.
Thank you.
I think I have it that so that you can only get it with the link.
Question.
Yeah,
so
friend
I'm
request.
in your class right after this. Is it in the same Zoom room?
Yeah.
Okay.
You can just stick around.
Mistress Da Costa, will you have this video that's being made available to other people, or is it just for your resource?
I will upload it and link it in the University of Atlantia listing for the course.
Wonderful. Thank you.
No problem.
So we just hang out here for taking your geometry class.
Yep, I'm going to stop the recording for this one.